So next we will move on to another concurrency control protocol, which is a timestamp based, and very importantly this does not use locks, it is a lock free protocol. So this protocol is called the timestamp ordering or the TO protocol. So timestamp ordering protocol, this is very importantly this is lock free, so it does not use any lock on the data item. Alright. So first of all, what is a timestamp? So each transaction is assigned a particular timestamp when it starts. So when the transaction starts, it is assigned a timestamp. So this is called the TS of T is essentially the timestamp of T. So a timestamp is a logical counter, it is a logical time, it can be the actual wall clock time or any logical counter such that this is ordered, this is, so the timestamps are ordered and it is any logical clock. So this is an ordered logical clock. So very simply every time tick may be given an unit, the timestamp 1, then 2 and so on and so forth, and it can be anything as long as it is ordered, and ordered meaning, so between two timestamps it can be always determined whether the timestamp of the first timestamp is lesser than the second timestamp or equal, that can be always done. So that is what it is ordered. Okay. So that is the timestamp for the transaction. So this is when it starts. So when the transaction starts, that is given a timestamp, that is the timestamp of the transaction. Now for every data item X, so there are two timestamps that are maintained. The first one is called the write timestamp, which is the largest timestamp of any transaction that wrote X. Okay. So that wrote X successfully, but essentially, so what does it mean? That X is the data item and suppose transaction 1 wrote it and transaction 2 wrote it both. So it is the largest timestamp. So in the transactions, if transaction 1 starts before transaction 2, then the timestamp of transaction 1 will be less than the timestamp of transaction 2, that is because it is ordered, etc. And if both of them suppose has written to an X, then this will get the largest timestamp. So this is important, that this is the largest timestamp of any transaction that has successfully written to X. And similar to the write timestamp, there is of course a read timestamp, which is the same definition. It is the largest timestamp of a transaction T that successfully read X. Okay. So once more, this is the largest timestamp of something that has wrote to X and these things. So the timestamp ordering protocol uses only this timestamp. So it only uses the timestamps, and we will see that, but essentially it can be shown that so the protocols that use timestamps can never deadlock, because it so there is always a strict ordering between the transactions that has started. So transaction 1, if it starts before transaction 2, it must be having a lower timestamp than ordering 2, and so it can never deadlock because there is an implicit priority order of the transactions based on the timestamp. So timestamp ordering protocol, or for that matter any protocol that you can think of that uses timestamps, will not deadlock. So this is a very important property of it. Anyway, so coming to the actual protocol, what it does is that the basic idea of that is that the conflicting operations, the basic philosophy of the timestamp ordering things is that the conflicting operations are executed in the timestamp order, are executed in the timestamp. So if there are two operations I1 and I2, and then I1 if has a lower timestamp, then it is executed in that particular order, are executed in timestamp order. So this is the important part of it. This is the of course the intuition of the philosophy of what the timestamp ordering protocol is, and we will go to the details of it next. So suppose this is the thing. So a transaction requests a read. Note that this is a request because it may or may not successfully end doing it, correct. So it just requests a read on X. Okay. Now couple of things may happen, is that the following things may happen, is that if transaction the timestamp of transaction T is less than the write timestamp of X, then what is the essentially the meaning is that the write timestamp of X essentially says that there is a transaction. What is the write timestamp of it? It is the timestamp of a transaction that has written to X, and that transaction is greater. So the timestamp of that transaction is greater than the timestamp of this transaction T. That means that that write has essentially shouldn't have happened before this read. So essentially this read is late and there is somebody written, some other transaction which was supposed to write later has already written, and only now the read request for this transaction is coming. So this is not correct, because this is now going to read, if it now reads, it is going to read what has been written by the timestamp, the WTS of X. So just to elaborate this further, so suppose the write timestamp is essentially the timestamp of some other transaction T1 that has written. So essentially transaction of the timestamp of this T is less than the timestamp of the transaction 1 that has written. So it should have read the value before T1 got a chance to write it. So it has not done it, so this is wrong. So this operation, this is not going to be allowed. So what it does is that this request is rejected, and so this is this request is rejected, and this T or T1, whichever one of them, must be rolled back, because okay, they have not done it in the order that they were supposed to do. So T, the read of T should have happened before the write of T1, but they have not done. So either this happens. So this is not correct. So essentially this is the whole point. If this happens, then this is not correct. So then it cannot allow. So this request is rejected. This is very, very important. So this request doesn't go through. All right. On the other hand, if the timestamp of transaction T is greater than the write timestamp of X, which is, let us say, that of some other T2, then there is no problem, because T2 was supposed to write to this X before TS has read, because the timestamp of T2 is lesser than the timestamp of T, and that is what is being done. So this is fine. So this is simply request is granted. Request is granted meaning that T is allowed to read X, which also means that the read timestamp of X need to be updated. So the read timestamp of X is then updated to the, so it is the largest read timestamp, right? So it's either the whatever it's already there or the timestamp of T. So essentially if the timestamp of T is greater than the read timestamp, then it is updated, otherwise it remains the old thing. So that is the thing. So but this is very importantly, this is granted. Correct? So that is the read request. That is what happens when the read is, when a transaction T requests a read. Okay. The next thing is when a transaction T requests a write. So this is again just a requests a write of X. Okay. The first thing is that if the transaction, if the timestamp of T is less than the read timestamp of X, suppose this is equal to some timestamp of T1, right? This means that again the same problem as in the earlier case. So the read of timestamp T1 has already read it. Now T1 shouldn't have read before T has got the chance to write, because T is earlier. The timestamp of T is lesser than the timestamp of T1. So T should have written before this the read of X by T1 has done. So this again, this is wrong. This should not be allowed. So this write request is rejected. This write is rejected, and the same thing is that T or T1, one of them is rolled back. That is the same idea, because there is a read write conflict and it has not progressed in the correct order. So this is rejected. So this does not go through. Okay. The second one is that if the timestamp T is less than the write timestamp of X, let us say this is the timestamp for T2. Okay, again the problem is T should have written before T2, correct, because the timestamp of T is lesser than the timestamp of T2. So, the write to X for T should have happened before the write of X by T2. So, the same thing. So, this write is again rejected. It is a write-write conflict, the previous one was a read-write conflict. So, this is again rejected, and then the same thing is that T or T2 is rolled back, correct. So, this is rejected and this operation this does not go through. And finally, transaction T is greater than transaction the read timestamp of X, and transaction the timestamp is greater than the write timestamp of X. So, which means that there is no problem. All the reads that should have gone earlier has all gone earlier, and all the writes that has gone earlier has gone earlier. So, this is simply allowed. So, write is granted, and similar to the previous case, the write timestamp may now need to be updated. So, the write timestamp of X needs to be updated, but now you see that the write timestamp is just needs to be updated to T, because there cannot be any other write timestamp which is greater than T. So, simply this can be taken as the write timestamp of T. So, that is the two things. So, these are the two important parts. If that when T requests a read and a write, then what happens essentially. So, very simply, if a transaction comes after and then it is in the correct order, then it is granted, otherwise it is rejected. Okay. Now, all this is fine. We now need to argue a little more formally about the correctness. Why is this going to be correct? So, the correctness of the timestamp ordering protocol can be argued. So, this first of all, this guarantees conflict serializability. So, this guarantees conflict serializability. That is not probably very hard to see, because it does not allow any conflicting operations to go through. That is the whole idea of the protocol. Why it rejects these things? Because it was violating those conflicts. So, that is the thing. And essentially the idea is that the conflicting operations are executed in the correct timestamp order. If it is not, then if it appears, so if it is requested in a if it does not appear, if it appears in a non timestamp ordering what it should be, then it is rejected. Okay, that is the first thing. The other thing is, as I said, there cannot be any deadlock, because the transaction that started earlier always gets a priority. So, all these things, the transaction with a smaller timestamp is always going to get the priority. So, deadlock free. So, this is called a deadlock free. So, but there may be starvation, and what it happens is the same situation is that the timestamp there may be other transactions with lower timestamp that keep on coming, and the particular transaction is just keeps on waiting indefinitely. It is always rejected, 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 and so on and so forth. So, it may cause starvation, okay, and it may not be. So, it is not cascadeless, which means that, so essentially it means that cascading rollbacks may happen, because a particular transaction aborts, the other transaction that is dependent on it may also abort. So, it is not cascadeless. In fact, it is very interestingly, it is not even recoverable, because it has it is not even recoverable because it has allowed a particular timestamp, it has allowed a particular transaction to go ahead and read or write, because the other transaction has not yet come, and that transaction maybe just have committed or aborted. So, it may have just committed and not aborted. So, then it is non-recoverable, because later you find that, oh, it should not have done this, but by that time it has already committed. So, this is very important, that this is not recoverable. So, although it is deadlock free and it guarantees conflict serializability, it still has these problems of starvation and not recoverability. Of course, if it is not recoverable, it is not cascadeless as well. So, there are certain modifications, just like there are variants of the two-phase protocol, there are certain modifications that can be done to the basic timestamp ordering protocol. Okay. First of all, you can use something called a commit dependency. There is a concept of commit dependency. So this is to essentially ensure that the transaction, the schedules are recoverable. Okay, what is the commit dependency? Is the following: if Ti reads from Tj, then Ti has a commit dependency on Tj, which is essentially saying that, so the dependency on Tj. So that means that if Ti reads from Tj, what does it mean is that, so Tj has produced a value, so Tj has written a value which Ti reads, then Ti has a commit dependency on Tj, which means that Ti cannot commit unless Tj commits. So it commits depends on whether Tj has committed or not. So that is called that commit dependency. So this essentially ensures, this is to ensure that Ti does not commit before Tj does. It does not commit because it is dependent on Tj. So unless Tj commits, it cannot do it. It does not commit before Tj. That is to ensure that the it is recoverable, the transaction is recoverable. Otherwise what may happen is that Ti reads and then commits and then Tj aborts, but by the time Ti has already committed, and it is a wrong commit because Ti has read a value that it should not have done. So that is what this thing, correct? Okay, now couple of more things. So now to make these things recoverable and cascadeless, so this is to making this recoverable and cascadeless. So there can be certain modifications done to this thing to make this recoverable and cascadeless. What can be done is that all writes are performed in the end, all writes are performed in the end atomically, are performed atomically in the end. So again, what does this atomically mean is that either all the writes go through or none of the writes go through, and that is done in the end. So that is essentially just saying that none of the writes will be done unless all the writes will be done, and that will be done in the end. So first you read all of these things and then the writes is done. Now if this cannot be done, if a transaction aborts, then what happens? If a transaction aborts, then it just restarts with a new timestamp. So that means you will get a higher timestamp, and then the commit dependencies etc. and the commit and the timestamps, because it will now start with a higher timestamp. All the transactions that started earlier will get a priority over this, and because it has aborted, and then it will just try to finish it as that way. Okay, so that is one way of doing it. The other way of doing it is that, okay, so let me just write it down. So transaction restarts with a new timestamp if it aborts. So it's a new timestamp if it aborts. So these are the two important things. The other way of making this is to use the locks, but then that is, you see, that is going against the philosophy of why timestamp ordering protocol is needed in the first place, because it is supposed to be lock free, and then so to use locks to make it recoverable and cascadeless is essentially just having a locking kind of protocol. So that is not a very elegant solution or good solution. Anyway, and then there is one version of it which is called a strict timestamp ordering protocol, which is, this essentially tries to make the protocol strict, just like there is a strict version of the 2PL. Essentially this waits for data to be committed. So this essentially waits for data to be committed before it is read or write. So wait data to be, so it essentially does not read or write any uncommitted data. So it only reads committed thing. So that is essentially just mimicking the definition of strict schedules. So it will only read or write a particular data for which the transaction which produced read or write that thing has committed. So that means that is all correct, and then only it reads and writes. So that is all serial. So that is this is about the timestamp ordering protocol. There is one extra thing that can be done, which is called the Thomas's write rule. So Thomas's write rule is to make it a little bit more concurrent. So it is to allow some more schedules which will not be allowed by the basic timestamp protocol. So remember what we did for conflict serializability to view serializability. We did not take care of the blind writes. So the blind writes were okay. So here the same thing. So obsolete writes. So it's not essentially blind write, but obsolete writes. Obsolete writes are ignored. So if there is an obsolete write, it is simply ignored. So what does an ignoring of an obsolete write mean is the following thing. You remember what happens in the write case is that if the transaction that wants to write has a timestamp lesser than the read timestamp of this. So suppose this transaction is T2, then in the basic timestamp ordering protocol this was rejected because this is essentially the writes have not come in order. In this case, in the Thomas's write rule this is allowed. In the Thomas's write rule this is allowed, nothing, because the idea here is that T is trying to write an obsolete value. Okay, why it is an obsolete value? The reason this trying to write an obsolete value, why is this called an obsolete value? Because you see what is happening is that T, suppose T would have actually retained the value of x. Now there is another transaction 2 which would come after T because the timestamp is raised and would have retained x anyway. So that write by T will be overwritten by the write by T2. So this was obsolete anyway, so this is why it is obsolete, and in okay, it is not a problem if an obsolete write was not sent, so you simply ignored. So you simply ignored that there was an obsolete write and that was not written, so he simply ignored the loss of an obsolete write because it was obsolete anyway. So then this is allowed and then that protocol just goes through. So what it essentially means is that instead of in the 3 conditions of the write rule, 2 of them doesn't pass and the 1 pass, this the middle condition is also made pass because it is an obsolete write and the obsolete write is ignored. So this increases the concurrency, this increases the concurrency of this because it allows some more writes to go through, so it allows some more transactions to go through to successfully complete and commit, etc. It increases concurrency, it also increases the recoverability because now what happens is that this transaction will not simply abort, it can continue. So it may be increasing the recoverability. So as a note on this, so this allows certain view serializable things. So this can allow certain view serializable schedules which will not be allowed otherwise by the basic time thing. Because as you see, this is essentially the obsolete rule is the obsolete write is essentially the difference between conflict and view serializable things. So here is a very small example that will highlight this. So suppose this is R1A, W2A, W1A and W3A. Now you see that this W2 is obsolete write and this will be allowed under this Thomas's write rule but not otherwise, and this protocol this goes through. So that is the end of this timestamp ordering protocols.